Hey everyone, welcome to a video on factoring product of binomials. What's that mean? Let's find out. So we've spent the last couple of weeks looking at these two um, like games almost, like activities, diamond puzzles and algebra tiles. And we've been like finding numbers that add up to 7 and multiply to 6, and we've been taking these pieces and rearranging them into rectangles, and it's like, what does this have to do with factoring? What do these have to do with factoring? And the reason why that question seems like such a natural one, right, is because we have looked at greatest common factor factoring, where we take an expression like 2x cubed minus 8x, we say, oh, well, those have a greatest common factor, which would be 2x. And then we've learned how to factor this expression into 2x times x squared minus 4, right? This is this first type of factoring that we've learned. And this doesn't seem to have much in common with algebra tiles and diamond puzzles. But there's another type of factoring that we're going to really look at today. And we're going to find out it does have a lot to do with algebra tiles and diamond puzzles. And it's called product of binomials. And product of binomials is a technique that we would use to factor something like this expression here, right? X squared plus 9x plus 20. Looking at that, we can see there's no greatest common factor. Now, what does product of binomials mean? Well, product means multiplication, and binomials, right? This bi part at the start of it, right, means two. And so a binomial is actually an expression that has two terms. And so when you find a product of binomials, you find a multiplication of two factors that each have two terms. In this case, this expression, x squared plus 9x plus 20, would factor to x plus 5, x plus 4. Now let's stop for a second. I claimed that this has a lot to do with algebra tiles and diamond puzzles. Let's see how that's the case. Well, let's look at a diamond puzzle. X squared plus 9x plus 20. I'm just going to take two of these numbers, the 9 and the 20, put them in the puzzle. Oh, that's not what I wanted to do. I wanted to do this, 20 and 9. And then I ask myself, what two numbers multiply to 20 and add to 9? Well, that would be 5 and 4. Hey, look at that. There's a 5 over here, and there's a 4 right there. Let's look at some algebra tiles, right? So here we have an algebra tile diagram, right? And if we count this very carefully, I think we would see that this has one x squared tile, 1, 2, 3, 4, 5, 6, 7, 8, 9 x tiles, and that's 20 little 1 tiles, which is exactly x squared plus 9x plus 20. And let's look at these lengths here. Well, this length right here is, that's x plus 5, right? And this top length of here is, haha, x plus 4, which are the exact factors, where there, the exact factors we got when we factored this. And so, like, we could have maybe just told you that this is a trick, right? And you do this thing and you get that. But the problem is that then we wouldn't really understand what we're doing. So, like, when factoring an expression into product of binomials, we find the two values that add to the x coefficient and multiply to the standalone coefficient, which is the practice that we got from working with diamond puzzles. That's why we worked on diamond puzzles, is to practice this process. And when we're factoring, we don't change the expression's value. We're just rearranging it. And that's part of the reason that we spent a while on algebra tiles, to see what we're doing when we factor. Because if it just looks like we're moving around letters and numbers, that's not really doing math, okay? So we spent this time with algebra tiles, we spent this time with diamond puzzles, building up to a place where we can actually start factoring things like x squared plus 9x plus 20 into these two different binomial terms. And our goal is to factor into product of binomials without using diamond puzzles or algebra tiles anymore. They've been like a support for us so that we can get good at this and know what we're doing. That's kind of been our goal. Now here's an example of an expression that we could factor into a product of binomials. X squared minus 11x plus 28. Now the question that I'm asking myself when I look at this is, what two numbers add to negative 11 and multiply to 28? That's that diamond puzzle part of it. And so I'm going to take this 28, right? I'm going to find the factors. Now I know I need to use negative factors because they have to add to negative 11 and they have to multiply to a positive number. So they have to both be negative. So I'm like negative 1, negative 28. That's too big. Negative 2, negative 14. Those don't add up to negative 11. Negative 4, negative 7. Oh, those do add up to negative 11, actually. And so I think what this would be equal to, right, would be x minus 4, x minus 7. We just factored it. We factored it using our understanding of diamond puzzles. And we know that all we've done is we've just said, hey, like these are like the lengths of the rectangle that make that up these pieces. We could check by doing double distribution, right? So if I multiply each term by each term, we would end up getting back to x squared minus 11x plus 28. Now, a couple quick tips and tricks for this to make sure that we're not making common mistakes, right? So the first one I would say, careful on mixing up the addition and the multiplication. That matters. It's adding up to the x coefficient and multiplying to the last value. So it has to add to negative 11 and multiply to 28. Both these binomials need parentheses. If you were to write this without the parentheses, that's a very, very different thing. So you can almost think of the first thing that you're doing is you're just creating two sets of parentheses and then you're finding the binomials. Y'all, please don't assume that it's x. Look down here. We can already see, here's an example where the variable is not x, it's y. Okay? And the last thing is the order of the factors doesn't matter. So if you had factored this expression up here, and instead of getting x minus 4, x minus 7, if you had gotten x minus 7, x minus 4, that's fine. That's the same thing. The order doesn't matter because it's multiplication. Okay? Let's look at two more examples, just a little practice. Y squared plus 3y minus 10. Okay, so I'm going to factor this. I'm thinking to myself, I need to add to positive 3. I need to multiply to negative 10. Maybe I'm going to make a little table again. So negative 10, 1 and negative 10. Those don't add to 3. 2 and negative 5. Those add to negative 3, but I need to be positive 3. 5 and negative 2. Hey, those add to 3. I therefore know that this should factor to y plus 5, y minus 2. Let's check it this time because we really want to make sure that we're not assuming that we're doing all this arithmetic correctly. It's easy to make mistakes here. So that becomes y squared minus 2y plus 5y minus 10. Combine those like terms, and that should be y squared plus 3y minus 10. And we're good. It worked, right? I'm using my diamond puzzle logic to do this. One more example. A squared plus, look at that. Look at that. Don't assume it's x, everybody. A squared plus 17a plus 72. Oh, man. Now notice, you wouldn't want to actually solve this one with algebra tiles because it would need 72 of the little squares. It would take a long time to work with. But we know that we can just think, okay, I need to add to 17. I need to multiply to 72. So I take 72. And maybe you're at a point where you can like think through the factors of 72 in your head. But if you're not, this is what I would do. 1 times 72, that's way too big. 2 times, maybe get my calculator, divide 72 by 2. Oh, 36. That's way too big also. 3 times 24. That's too large. I keep going, right? 4 goes into 72. 4 times 18. Okay, that's 22. I'm getting closer. 6 times 12. Oh, that's 18, but I need 17. And 7 doesn't go into 72 evenly. I check it on my calculator. Oh, 8 times 9. 8 plus 9 is 17. So I say, haha, I know how this factors. It factors into, put my two parentheses there, a plus 9, a plus 8. Boosh. Ask us your questions if you got them. Have a good one.